Before diving into the world of security within development pipelines, it is essential to understand what DevOps is, why it was created, and how the concept of DevSecOps grew out of it. You have already explored the foundational pillars of cybersecurity, confidentiality, integrity, and availability, as well as common web threats. Now, this course connects those concepts to the real-world environment where software is built and delivered, the DevOps pipeline. What is DevOps and why does it exist? For decades, software development was organized in two separate worlds that rarely communicated well. On one side, you had the development teams, whose job was to write code and deliver new features as quickly as possible. On the other side, you had the operations teams, whose job was to maintain stable, reliable systems in production. These two groups had fundamentally opposite priorities. Developers wanted to change things fast, while operations teams wanted to change things as little as possible to avoid breaking what was already working. This friction created a well-known problem in the industry. Software took months or even years to go from an idea to a live product. Bugs discovered late in the process were expensive to fix. Deployments were stressful, manual, and error-prone. The result was slow delivery cycles, frustrated teams, and unhappy users. DevOps emerged in the late 2000s as a cultural and technical movement designed to solve this problem. The word itself is a combination of development and operations. The core idea is simple. Break down the wall between these two teams, encourage them to collaborate continuously, automate repetitive tasks, and deliver software in smaller, more frequent increments rather than in large, risky batches. To make this possible, DevOps relies on a set of practices and tools that automate the journey of code from a developer's workstation all the way to production. This automated journey is called a pipeline, and it typically includes steps such as writing code, testing it automatically, building the application, and deploying it to servers, all in a fluid and repeatable sequence. The key concepts behind DevOps. To fully grasp DevSecOps, you need to be comfortable with the following DevOps building blocks. Continuous integration, often abbreviated as C, is the practice of merging developers' code changes into a shared repository several times a day. Each merge triggers an automated process that compiles the code and runs automated tests to detect problems early. For example, if a developer introduces a bug by modifying a login function, the C system will catch it within minutes rather than weeks. Continuous delivery and continuous deployment, often referred to together as CD, extend this idea further. Continuous delivery means the code is always in a state where it could be deployed to production at any time, even if the actual deployment still requires a human decision. Continuous deployment goes one step further. Every change that passes all automated checks is deployed to production automatically, without any human intervention. Large companies like Netflix or Amazon use continuous deployment to release code thousands of times per day. Infrastructure as code is another key concept. Instead of manually configuring servers by clicking through interfaces or running commands by hand, infrastructure is described in configuration files that can be versioned, reviewed, and applied automatically. Tools like Terraform or Ansible are widely used for this purpose. This makes environments consistent and reproducible. Containers are a modern packaging method that bundles an application with everything it needs to run, libraries, dependencies, configuration, into a single portable unit. Docker is the most well-known container technology. Containers solve the classic problem of it works on my machine but not on the server by ensuring the environment is identical everywhere. Orchestration tools like Kubernetes go one step further by managing large numbers of containers automatically, starting them, stopping them, scaling them up or down based on demand, and recovering from failures. Why security was left behind in DevOps. With all these automation tools and fast delivery cycles, DevOps dramatically improved speed and reliability. However, there was a significant problem. Security was not part of the conversation. Security teams were typically brought in at the very end of the development cycle, just before a release, to perform security checks. This approach, sometimes called security as a gate, created serious issues. First, when security problems were found at the end of the process, they were extremely expensive and time-consuming to fix, because the code was already written, tested, and almost deployed. Second, developers had little awareness of security vulnerabilities while writing their code, so the same mistakes were repeated over and over. Third, the speed of DevOps pipelines made it nearly impossible for a small security team to manually review every release. The result was that many applications were deployed with known or unknown vulnerabilities, putting users and organizations at risk. Think back to the common web threats you studied earlier. Things like injection attacks, broken authentication, and cross-site request forgery. These vulnerabilities are often introduced at the code level, during development, not after deployment. Catching them late means the damage may already be done. The birth of DevSecOps. DevSecOps is the direct answer to this problem. The term stands for Development, Security, and Operations, and it represents the idea that security must be integrated into every stage of the software development and delivery process, not added at the end. The central principle of DevSecOps is often expressed as shift left. In a traditional pipeline, time flows from left to right. You write code, then you test it, then you do security checks, then you deploy. Shifting left means moving security activities as far to the left as possible, ideally starting with the developer writing code, or even before that, during the design phase. In a DevSecOps approach, security is no longer the sole responsibility of a dedicated security team. Every person involved in the pipeline, developers, testers, operations, engineers, shares responsibility for building secure software. This does not mean everyone becomes a security expert, but it does mean everyone must be aware of basic security principles and use tools that automatically flag security problems as they work. How DevSecOps works in practice. DevSecOps introduces specific automated security tools at different stages of the pipeline. Here is what this looks like concretely. Static Application Security Testing, commonly known as SAST, analyzes the source code of an application without actually running it. It looks for patterns known to be dangerous, for example, a piece of code that builds a database query by concatenating user input directly, which is a classic SQL injection vulnerability. SAST tools can be integrated directly into the development environment, so a developer gets a warning the moment they write problematic code, much like a spell checker flags typos. Dynamic Application Security Testing, commonly known as DAST, works differently. It actually runs the application and sends it simulated attacks to see how it responds. This is closer to what a real attacker would do. For example, a DAST tool might attempt various injection payloads against a login form to see if the application is vulnerable. DAST is typically used later in the pipeline, when a running version of the application is available in a test environment. Software composition analysis is a third category of security tool used in DevSecOps. Modern applications are not built entirely from scratch. They rely heavily on open-source libraries and third-party components. Software composition analysis tools automatically scan these dependencies and check them against databases of known vulnerabilities. For example, if your application uses an old version of a popular library that has a known remote code execution flaw, the software composition analysis tool will alert you immediately. Secret scanning is another practice integrated into DevSecOps pipelines. Developers sometimes accidentally include sensitive information, passwords, private keys, API tokens, directly in their code or configuration files. Secret scanning tools automatically detect this before the code is committed or deployed. Threat modeling is a more strategic practice, usually done before development begins. It involves analyzing the architecture of a future application and identifying where the most significant risks are, so that security measures can be designed in from the start rather than patched in later. The DevSecOps culture, not just tools. It is important to understand that DevSecOps is not only about adding security tools to a pipeline. It is fundamentally a cultural shift. In organizations that truly practice DevSecOps, security champions are embedded within development teams to share knowledge. Developers receive regular training on secure coding practices. Post-incident reviews, when a vulnerability is discovered or exploited, are treated as learning opportunities rather than blame sessions. Security requirements are written as part of user stories alongside functional requirements. For example, a development team building a user authentication system would not just write requirements like users should be able to log in with email and password. They would also write security requirements such as passwords must be stored using a strong hashing algorithm and failed login attempts must be rate limited to prevent brute force attacks. These requirements are then validated automatically as part of the pipeline. The link between DevSecOps and your future role. As a future cybersecurity and DevSecOps specialist, you will operate at the intersection of all these practices. You will need to understand how applications are built and deployed so that you can identify where vulnerabilities are most likely to be introduced. You will use tools like Nmap for network reconnaissance, Wireshark for traffic analysis, and Metasploit for exploiting known vulnerabilities in controlled environments, but you will also need to understand how to integrate security checks directly into delivery pipelines using static application security testing, dynamic application security testing, and software composition analysis tools. You will be expected to produce vulnerability reports that developers can actually act on, which means understanding both the technical detail of a flaw and its place in the development lifecycle. You will also be expected to help teams set up non-regression tests, automated checks that ensure a vulnerability, once fixed, never silently reappears in future releases. This course has laid the conceptual foundation. From here, every technical topic you study, penetration testing, secure coding, container security, pipeline configuration, will make more sense when you understand that DevSecOps is the framework that ties it all together. Security is not a destination reached at the end of a project. It is a continuous practice, built into every commit, every test, every deployment.